The Big Bang. It's the story we often tell of our universe's fiery birth. A single, incredibly hot, dense point, exploding outward, ever outward, cooling over billions of years, forming stars, galaxies, everything we see. This is the standard cosmological model, a powerful theory indeed. But is it the only story, or the complete one? Cosmic questions still echo in the vastness. We humans are curious creatures, scientists especially so. We're always probing, always questioning the known. What ignited that initial, unimaginable spark? What existed, if anything, before the Big Bang? The very concept of a singularity, that initial point. An infinitely dense, infinitely small speck. It's where our current physics stumbles, where our equations break down even. So we search for new pathways, new cosmic narratives to explore. Imagine a universe unfolding, perhaps without those mysterious placeholders. Dark matter, often invoked as an unseen gravitational glue. Dark energy, an unknown force accelerating space apart. What if the cosmos doesn't strictly need them? At least not in the way we've traditionally thought. New theories are emerging, bold and wonderfully inventive. They seek to explain the universe's breathtaking grandeur, using physics we already grasp, or physics just within our reach. A simpler, more elegant cosmic dance. So, let us journey together to the very frontiers of human thought, where new ideas about our cosmic origins are taking shape. Consider Dr. Richard Lue's striking proposal, a universe born not in one cataclysmic bang, but in a series of startling, repeating bursts of creation. Or ponder Enrique Gastanaga's compelling vision, our entire cosmos, all of spacetime, emerging from the unfathomable depths of a black hole. These are mind-bending, challenging concepts. Let's dive in and explore these wonders. Dr. Richard Lue, a physicist at the University of Alabama in Huntsville. He presents us with a radical, thought-provoking alternative. Forget a single, solitary Big Bang event. Picture instead a sequence, a rhythm of creation. He calls these events temporal singularities. These are not specific points in space, but pivotal moments in time. Brief, yet immensely powerful, universe-wide flashes of becoming. A repeating pattern that underpins existence. A cosmic heartbeat, pulsing through the eons, if you will. This suggests a universe constantly refreshed. What are these temporal singularities like in Dr. Lue's model? Imagine the universe winking, almost imperceptibly, rapidly flickering in and out of an intensely high-energy state. These bursts of creation are so incredibly fleeting, so extraordinarily fast by our everyday standards. We cannot hope to observe them directly with our current telescopes. Yet, each wink, each distinct temporal singularity, is theorized to flood the entire cosmos anew, with torrents of fresh fundamental matter and vibrant propagating waves of primordial energy, a constant, subtle, underlying renewal of everything. This innovative perspective changes our cosmic recipe quite significantly. Perhaps, Lue suggests, dark matter isn't an essential ingredient, to explain why galaxies clump together in the majestic way they do. These repeating bursts themselves could provide the raw material, and also the necessary gravitational seeds for structures to form. What about the universe's perplexing, accelerating expansion? Lue proposes these singularities inherently generate a negative pressure, a natural, intrinsic, repulsive force pushing everything apart. This effect would skillfully mimic dark energy's observed role, without needing a separate, unknown energy field. This bold vision starkly contrasts with the standard cosmological model, one primordial, universe-birthing explosion versus countless energetic pulses. Dr. Lue's earlier theoretical work, published in 2024, already hinted at the controversial idea of gravity existing without mass. This newer model, further refined and presented in 2025, is even more elegant. It endeavors to explain cosmic phenomena without invoking overly exotic concepts, such as negative mass or forms of negative density. And perhaps the most exciting part? Tests to validate or challenge this model might be possible, using highly sensitive instruments right here on our home planet, Earth. Now let's shift our gaze to another fascinating alternative genesis. This one is proposed by Enrique Gastanaga from the University of Portsmouth. What if our universe, our vast sprawling home, all the stars, all the galaxies, all of known existence, was actually born inside a black hole? Pause for a moment. Contemplate that astounding idea, the entirety of our experienced reality. emerging from what we often consider to be an ultimate point of no return, a gravitational prison. This would be a truly grand cosmic escape. How could such an extraordinary event ever happen? The proposed mechanism is poetically called a bounce. Imagine a colossal cloud of primordial matter, incredibly dense, collapsing under its own immense gravitational pull, much like in the conventional formation of a stellar black hole. Normally, our physics would predict a singularity at the very center, a point of theoretically infinite density and zero volume. But here, the strange and wonderful rules of quantum mechanics intervene. The Pauli exclusion principle, applied to fundamental particles, forbids such an infinite squeeze into nothingness. So the collapsing matter bounces, rebounding outward with incredible force. This black hole bounce model isn't just pure speculation or fantasy. It is commendably grounded in well-established physical theories. Einstein's general theory of relativity, our best description of gravity and space-time, and the laws of quantum mechanics, the fundamental rules of the very small. Working in concert, these pillars of modern physics offer a natural explanation for the universe's initial, extremely rapid period of inflation, and also for its current, mysterious, accelerated expansion, an expansion often attributed to the enigmatic dark energy. This model suggests an intrinsic source for these cosmic dynamics. No extra unknown fields required to drive the show. This elegant framework also tackles some of the biggest unresolved questions in cosmology. Why is our universe so remarkably geometrically flat on large scales? Why is it so incredibly smooth and uniform across vast cosmic distances? How did it manage to get to be so mind-bogglingly vast? The specific physical conditions created by the bounce itself could provide the precise answers to these enduring puzzles, setting the initial state of the universe just right. It might even shed crucial light on the mysterious origins of supermassive black holes, those gravitational behemoths that lurk at the centers of most galaxies, offering a comprehensive, deeply interconnected picture of cosmic evolution. These two novel theories, Dr. Liu's repeating bursts and Dr. Gastanaga's cosmic bounce, they offer us compelling new answers, fresh perspectives, to some of the most age-old cosmological questions humans have ever asked. How did the universe truly begin its grand expansion? How did the intricate, beautiful cosmic web of galaxies actually form? Both of these new models strive to paint a coherent picture that relies less on purely hypothetical, unseen entities, like the pervasive concepts of dark matter and dark energy, or at the very least, they reinterpret their apparent effects, using fundamentally different, though plausible, physical mechanisms. Consider the majestic galaxies, those swirling islands of stars. How did they come to be, scattered across the cosmic ocean? In Dr. Liu's dynamic universe, the repeating temporal singularities are proposed to act like continuous cosmic seeds, periodically injecting fresh matter and vital energy into the cosmos, allowing vast structures to coalesce and grow over billions of years. For Dr. Gastanaga, the specific physical conditions immediately following the bounce would have imprinted the initial subtle density fluctuations in the early universe. These fluctuations are the very blueprints for future galaxy formation. Both theories offer elegant, alternative narratives for cosmic structure. But are these just beautiful, imaginative ideas? Or can we, as scientists, actually put them to the test? Science, after all, demands rigorous evidence and falsifiable predictions. Dr. Liu is optimistic about the testability of his model. His theory of temporal singularities, he suggests, might be verifiable through incredibly precise earthbound laboratory experiments, looking for subtle, predicted effects on space-time or fundamental particles. Dr. Gastanaga's black hole bounce model, on the other hand, makes a very specific, observable cosmological prediction. It suggests our universe should possess a slight positive spatial curvature. Future cosmological surveys using powerful next-generation telescopes could potentially detect this distinctive signature. So why is it so absolutely crucial to explore these new explanations for the very beginnings of everything, for the origin of our cosmos? Because science is, at its heart, a relentless quest for deeper understanding. It thrives on boldly challenging established paradigms and cherished theories, on constantly asking that powerful creative question, what if? These new theories push the known boundaries of our collective knowledge. They encourage vital critical thinking and inspire new avenues of research. And they humbly remind us that the vast cosmos, still holds profound, captivating mysteries yet to be unveiled. Our amazing journey to comprehend our place within it is truly far from over. The universe with all its secrets awaits our inquiry.